are counting down toward today's launch of the STS-52 mission, and all is proceeding on schedule here in Firing Room 3 and out at Launch Pad 39B. We're standing by momentarily to have the flight crew in the suit-up room. And we've got Commander Jim Weatherby, Mission Specialist Charles Lacey Veach, Pilot Mike Baker giving a thumbs up for today. He's ready to go. Here's Mission Specialist Bill Shepard. He's the most experienced shuttle member of the crew today. He's making his third trip in the shuttle this morning. And here's Canadian Payload Specialist Steve McLean making his first trip aboard the shuttle today. And Mission Specialist Tammy Jernigan is getting her helmet on. Commander Jim Weatherby, Pilot Mike Baker. It's Mission Specialist Steve McLean. Tammy Jernigan, Bill Shepard, and Lacey Veach. Crew is now getting on board the astronaut van and will be taking about 15-20 minute ride out to Launch Pad 39B. This is the 195-foot level at Launch Pad B. The flight crew is making their way across the orbiter access arm to the white room, where they will be assisted by the closeout crew in getting ready for today's launch. Commander Jim Weatherby now greeting members of the closeout crew. He will be the first one to get inside the orbiter Columbia. Payload Specialist Steve McLean from Canada will be riding in the middeck of the orbiter. He is also being assisted right now by the closeout crew at Pad B. He is one of 6 Canadian astronauts selected in December of 1983. He was designated as the payload specialist to fly with the CanX-2 set of Canadian experiments that are flying on board Columbia. Pilot Mike Baker is now being assisted with his flight suit. He's a 38-year-old Navy captain from Lemoore, California, making his second trip aboard the shuttle today. Mission Specialist Tammy Jernigan is being assisted with her flight suit, getting ready to climb aboard Columbia today. Tammy and Charles Lacey Veach and Pilot Mike Baker are posing for pictures, and Commander Weatherby is making voice checks.
NPD on Air Ground 1, got you loud and clear.
Mission Specialist Bill Shepard is now being assisted to get aboard the shuttle. He's a 43-year-old captain in the United States Navy. He was born in Oak Ridge, Tennessee, and will be making his third shuttle flight as a mission specialist today. Team is continuing to stand by, and we will await to see if we get word that the weather is acceptable.
Columbia Launch Director. Air to Ground 1.
Idiot.
Okay, Jim.
Go ahead, sir.
All right, Jim. Well, it looks okay. I guess it's appropriate that we held the weather for the ex-weather coordinator, but we're comfortable to proceed, and if you are, we will do that.
Well, sir, it's probably a lot harder for you than it is for us. We've been having a good time sitting here, and thanks for all the work, and we are go.
The 3 main engines are being gimbaled and positioned for launch. In just a few minutes, the gaseous oxygen vent hood will be retracted.
Expected errors.
close and lock your visors, initiate O2 flow, and our thoughts ride with you today.
Okay, thank you very much.
T-minus 31 seconds.
Okay, let's go for auto sequence start.
Columbia's 4 redundant computers have primary control of critical vehicle functions for the remainder of the count. T-minus 20 seconds.
15.
T-minus 10,
Okay, let's go
9,
for engine start.
8. We have a go for engine start. 5, 4, 3, 2, 1. We have ignition and liftoff of Columbia on an ambitious 10-day international research flight.
Roll program, Houston.
Roger, roll, Columbia.
Houston now controlling. Columbia is rolled on course for its planned orbit. Columbia now traveling 600 miles an hour, 1 mile east of the launch pad, altitude 3.5 miles.
Columbia, Houston, go at throttle up.
Okay, Houston, go ahead, throttle up.
3 engines on Columbia now back at full throttle. Good hydraulic systems, good electrical systems. Altitude at 12 miles. Columbia is 9 miles east of the launch pad. Current speed 2,100 miles an hour. Columbia has now burned more than 2.5 million pounds of propellant since its liftoff. Shuttle now weighs less than half of what it did a minute and 50 seconds ago. Flight controllers now standing by for burnout and separation of the twin solid rockets. Booster officer confirms a good solid rocket booster separation. Altitude now 28 miles. Downrange from the Kennedy Space Center 34 miles. Columbia traveling 3,100 miles an hour.
2-engine banjo, Columbia.
Banjo.
And Columbia, Houston, performance nominal.
This is Mission Control Houston. This television from Columbia is a videotape taken yesterday of the opening of Columbia's cargo bay doors just after Columbia reached orbit. Currently on board the spacecraft, Commander Jim Weatherby is performing an alignment of the inertial measurement units. That's a daily job done on board during a mission, which uses stars to update the navigation constantly on board. Columbia's crew members, Mission Specialist Tammy Jernigan and Pilot Mike Baker and Mission Specialist Bill Shepard, are wearing shirts with the colors of the Italian flag in honor of the day's activities, deploying the Laser Geodynamic Satellite and the Italian Research Interim Stage Combination, which is a joint project between the Italian Space Agency and NASA.
Houston, Columbia, we're complete through step 3 of the deploy countdown. We'll hold off on mechanical sequence start until 23 minutes prior to deploy, unless you'd like otherwise.
Payload's copies.
We concur. We concur, Tammy.
Houston, Columbia for payloads. The PI and PSP setup is complete, and we're ready to begin the deploy countdown.
We copy, Tammy. And Tammy, you have a go for deploy.
Okay, they'll understand. Go for deploy.
Affirmative.
Houston, Columbia, mechanical sequence is active and the sun shield is opening.
Copy. We copy, Tammy, and we got a good view.
And in the aft portion of Columbia's cargo bay, the sun shield's protecting the A laser geodynamic satellite and its booster stages have now opened totally, revealing the satellite, and apogee kick motor, which is mounted atop the satellite. Also, still in the payload bay at the bottom of the satellite is the Italian research interim stage.
Should get the open indication.
Okay, I see stop motion now at 49
Okay.
seconds.
And I don't see the open there we are, open.
Satellite now working its way up to the proper revolutions per minute, currently spinning at about 60 revolutions per minute. Should get up to an area from 65 to 70 revolutions per minute. And the payloads officer reports now.
The grabbers are withdrawn. The spin table is at 65 RPM. Everything looks great on board.
Hey, we copy.
Payloads, everything.
We copy Tammy, and it looks good down here.
Live payloads, we see the fire command.
Copy, we see the fire.
Houston, Columbia, we see a good deploy, and we have phase lock and synced it.
Payloads, copy.
We copy. And Columbia, we understand a good deploy. Congratulations. A great job on deploying Legios.
Thank you, Houston, and arrivederci, Legios 2.
And we copy Columbia. Way to go.
Mission Specialist Tammy Jernigan is now going through procedures to safe the support equipment for the laser geodynamic satellite that's left in Columbia's cargo bay. Payloads officer here reports that the deploy looked very good from the ground, and that the laser geodynamic satellite and its accompanying boosters, the Italian research interim stage, and apogee kick motor all looked to be in very good shape.
Up forward of where Legios is our primary payload, U.S. microgravity payload. It's the first of a series of at least 6 U.S. microgravity payload experiments that will be flown on orbiters in the future. And I'll turn it over to Steve one more time, and he'll tell you about one of the experiments on USMP. The first experiment on USMP is the lambda point equilibrium experiment, and this is where the people from JPL are taking helium-4 from above a phase transition point to below a phase transition point. And this temperature where this phase transition occurs is at 2.17 degrees. And what is curious about this material is that as it goes below the phase transition, the entire helium goes into a single energy, which is a phenomena that is very difficult to obtain. We can obtain it on the Earth, but once we're in orbit, we're able to obtain that without the dirtying effects of gravity, and we should be able to get measurements around 10 to the minus 9 degrees as we cross this phase transition, and this is a very important measurement in terms of the quantum mechanical description of this material. Out on the end of the arm, we have a quartz crystal monitor and 2 different types of crystals. One we call just crystal A, and the other is crystal B. And what we're able to measure is the oxygen flux out in space, and this is probably the first time that we as astronauts have been able to see the atmosphere breathe as we cross the terminator, as the atmosphere actually expands as we go into daylight and then contracts as you go into the terminator. And we see a straight line on the screen right now, but that's because this is where we are in the data. But as we cross the terminator, these values go up and down. And just for your interest, the oxygen flux right now is 1.09 times 10 to the 15 outside the shuttle. And we have the temperature of the crystal is on the top, or is on the bottom set of data, and the frequency of the crystal is the top set of data here, and the oxygen flux is over on the right. And so probably for the first time we are watching the atmosphere breathe as we circle the Earth.
This is Mission Control Houston. This is the view of Columbia's mechanical arm as seen through the windows of the cockpit as the crew films and photographs the MELIO experiment, materials exposure in low Earth orbit. A set of 3 plates on the arm, which are filled with more than 350 different material samples. And one of the Canadian experiments on board to study how well those various materials hold up against the corrosive effects of atomic oxygen as atomic oxygen is encountered by them in Earth orbit.
This is Mission Control. This is a...
Sam, I never realized on my last flight, because I didn't have a guy like Steve explaining all this stuff to me, but the part of what looks to be the horizon there is really the top of the atmosphere, and you can see stars through the atmosphere there. I used to think that was the surface of the Earth there that you see glowing, but it's really the top of the atmosphere. The Earth horizon is in the picture a little bit higher, where the stars appear as they come up above the horizon. It's pretty amazing stuff on a moonless night to see the atmosphere glowing like that, and it really looks about just like that. That's almost a true reproduction that you see with your eyes. Steve tells me it's caused by joule heating. The atoms of oxygen smashing together, they get excited, they go up to a higher energy state, and when they relax, they give off photons.
This is Mission Control. This is a videotape playback of orbiter glow observations recorded by the crew earlier aboard Columbia. Commander Jim Weatherby has been giving us a description of what causes this phenomena.
We have a pretty exciting series of Canadian experiments with the Space Vision system that we will perform late in the mission with the Canadian target assembly out in the payload bay, and Lacey and Tammy will unberth that payload and take some measurements with the Canadian Space Vision system using that payload as a target. And they will be able to accurately position the arm, hopefully more accurately than we've been able to do so before with the existing instrumentation on board the orbiter. And hopefully the Canadian Space Vision system or a system like it will be used in the future for precise maneuvering of payloads or vehicles, such as construction of the space station or performing the rendezvous on the space station.
This is Mission Control Houston. This view is from the machine vision system for the robotic arm as it centers the Canadian target assembly. This view shows the display that an operator sees in the aft cockpit of Columbia as he moves the arm about a precise triangle above the cargo bay using the vision system for a guide.
away today. I'm tied up against the bulkhead here. What I'm currently in is the lower body negative pressure device. It's a medical experiment designed to assess the human body's ability to re-enter or readapt to the Earth's gravity. As you know, when we go up into space under the absence of gravity, the blood shifts from the lower extremities up to the upper extremities and to the head. The body perceives this as an increase in fluid, and it gets rid of the fluid up in space. Now, once we re-enter back down into the Earth's gravity, we essentially are fluid depleted, and so we have to be very careful and stay rehydrated when we're up here on Earth, when we're up here in orbit. This device I'll be in for another couple hours, I guess, and it's pulling a negative pressure of about 30 millimeters of mercury, and it's making the blood go back down to my lower extremities, and I can fluid load. It's a simulation of what will happen on re-entry. I'll turn it over to Shep, and he'll tell you a little bit about what he's doing.
Well, mostly what I'm doing right now is running a furnace. I'll talk about it in just a second, but I'm tracking Jim Weatherby's vital signs on a computer just to keep track as we do this negative pressure on his lower body, just to make sure that we keep him healthy. We're doing it on the screen on the left. On the right, I've got a grid computer that's controlling a furnace over to my right. It's the first time we've flown this on the shuttle. And it's an experiment. We have two furnaces inside. They're running at fairly high temperatures, upwards of 850, 900 degrees centigrade. There are two samples in each side of the furnace, and what we're trying to do is we're trying to grow crystals by heating the materials up high enough where they become vapor and then crystallize in one solid crystal. And it's sort of new technology, and hopefully this kind of process will give us the ability to commercially produce a lot of materials such as detectors and semiconductor devices that we don't enjoy the ability to do right now. And it's probably one of the most important commercial uses of space in the next decade.
Here we have an experiment that we'll spend a little bit of time on this mission. It may be the most important experiment that we do if we're successful, because what we're trying to do is to separate out white blood cells. We're trying to learn in this application how we can separate good white blood cells from cancerous white blood cells. And there's a neat little trick that allows you to understand the surface characteristics of a cell, and each surface wants to be in one particular chamber, and the cancerous cells will go in one direction and the normal cells will go in the other direction. And hopefully the resolution of this separation will be such that we can use this in what's called a bone purging technique. Technique is where you may have a child with leukemia, and you take out his bad cells along with his good, you separate them up in space, bring his good cells back down to the ground, irradiate the child just before you repurge his good cells in, and it may be a clinical application for leukemia.
Thanks. We photographed the land and the clouds and the water, not just for scientific purposes, but because they're very beautiful. As Bakes mentioned, we'll be coming up over Baja, California, and I've chosen the Linhof camera today. In order to take a picture, we set the time. I'm going to use 1/250th of a second. We set an f-stop, and Spock, our computer, is very helpful. It's telling us to set an f-stop of 8.0. So I'll set my f-stop, I'll point out the window, and I have a wealth of gorgeous targets because the Earth is always a beautiful view.
Here I have an instrument that follows the sun as it sets, and by pointing this instrument out the window at the sun, as it's setting in this fashion here, if the sun was there, then we can find out how much ozone is in the upper atmosphere. And this particular instrument will serve as a calibration basis for the World Ozone Network in the next couple of years. Okay?
Good morning. The heat pipe performance experiment comes out of Hughes Aircraft, and it has some very practical applications to the design of heat pipe systems which are used on commercial satellites. Heat pipes, quite simply, take heat and transport them from one place to another. For instance, on a communication satellite, from a hot electronics package out into space. There's not a great deal of data on the microgravity performance of heat pipes. And so during our mission, we're going to get some sort of idea of how well heat pipes perform in microgravity, meaning how well they transport heat. And we ran a series of tests this morning investigating the productivity of heat pipes. Some of the tests, the heat pipes were static, and for some of the other tests, the heat pipes were spinning, because as you know, some of these satellites in orbit are spin stabilized. And back to you, Jim.
Mission Control Houston, this is television live from Columbia as Mission Specialist Tammy Jernigan sets up the ergometer, or the stationary bicycle, in preparation for an exercise period. This television from Columbia's lower deck as Jernigan begins her exercise on the stationary bicycle.
This is Mission Control. This is video replay from Columbia of a test called DTO, or Detailed Test Objective number 657. It's footage that the crew has recorded of the operations of the new fan separator for the waste containment system. This is Mission Control. The legs with the socks on sticking out of the overhead area belong to Lacey Veach. She has an overhead panel pulled down in the middeck area performing the filter cleaning. This is a standard part of housekeeping aboard every shuttle mission. The crew opens the panels where the filters are located for the onboard air circulation system, and they inspect those for any debris or little particulate matter that may have collected there. If it's heavy enough, they clean it. If the filter is completely covered with debris, they may change it out. So that's what Veach is doing at the moment.
We were a little worried. Steve was a little worried about trying to fit in that pin block and damaging the pin. So we disassembled the battery box. And then routed the wires for the breakout box in through there, and then put the pin block back in. So I'm testing lead 1 and 2 right now, red to black.
This is Mission Control Houston. Mission Specialist Lacey Veach on the flight deck of Columbia is currently setting up the Sun Photospectrometer Earth Atmosphere Measurement Instrument. It's a handheld instrument that's used to measure the ozone and nitrogen compounds in the upper atmosphere by using a spectrometer.
They played the Monster Mash. It was a graveyard smash. It caught on in a flash. They played the Monster Mash. Out from his coffin, Drax's voice did ring. Seemed he was troubled by just one thing. Opened the lid and shook his fist and said,
"Whatever happened to my Transylvania twist?" Good morning, Columbia. Happy Halloween. And Columbia, be advised that we're trying to work some trick-or-treat time in today's flight plan for you.
Great.
And Columbia, we're with you on the flight deck.
Okay, thank you very much. This is Commander Jim Weatherby from the Spaceship Columbia. We'll be giving our final mission status summary. We've enjoyed giving them over the past week. It's been a great mission. It's been very rewarding for us, starting with, of course, the launch 10 days ago. It's a tremendous feeling riding on top of a rocket built by hundreds of thousands of people around the country and we all put our trust in those people, and they sure produced a great product. The vehicle has been outstanding. It's the 13th flight of Columbia in its history, and we've had so few problems, it's incredible. That enabled us to concentrate on the science, and I need to tell you that the science worked very well, too. All of the experiments worked the way they were built and designed and planned. We had a few minor problems. Steve McLean in particular was busy the whole week and a half trying to fix one particular experiment, which he finally was successful today, an experiment called SPEAM, and that finally worked. And so I think we ended up with about 100% mission success and all of our objectives met. We think the science return will be beneficial for several years to come, and it should keep the scientists very happy. The various experiments that we had some conflicting constraints down in the middeck, and it made it fairly difficult, but Mission Control in Houston made just a tremendous flight plan for us, enabled us to go from one experiment to the next, in some cases working experiments simultaneously. So we're very proud for the work that they did, and we're thankful that we were able to pull the mission off with as much success as we did. It's been a good mission for us. We hope to see you in a couple of years, and so from onboard Columbia, we thank you for listening for the past couple of days. And we hope to give you some more mission status summaries in a couple of years if we're lucky enough to fly again. And so happy Halloween from Columbia. Houston, we're not sure, but we think we may have a volcano in the center of your field of view now.
Okay, yeah, we copy. We see the same thing.
This is Mission Control. These camera views are from the
Coming up here on the
camcorder.
right, you can see some snow-capped peaks with the sun shining off of them. And all of those, if you look closely, are volcanic peaks.
Hey, Sam, that's that volcano we told you guys about last night, the one we saw smoking.
Copy.
This is Mission Control. Columbia is crossing the coastline of South America at just about between Chile and Peru. Then we'll go across Bolivia and a tiny little slice of Paraguay.
I think you can see the volcanic plume, or what we think is a volcanic plume, in the upper left quarter of the picture.
Houston, we're looking at the Hawaiian Islands. Attitude's not great to see, and we're doing the best we can.
I understand. Now we get a good view down here. Thanks.
This is Mission Control, Houston. Columbia is now moving out, about to move out across the Saudi Arabian Peninsula. In view of the payload cameras right now is the southernmost tip of the Sinai Peninsula. At the bottom portion of the screen, the long snaking line is the Nile River. Spectacular views like these are provided to us from the payload bay cameras of Columbia. This particular view is from an altitude of about 156 nautical miles. Now moving into view is the northern horn of Australia, also known as the Cape York Peninsula. This is Mission Control, Houston. Columbia is now passing over South America, and looks like there's some storm activity over that continent. The flashes that can be seen on the downlink is lightning crackling through the area. This area specifically is right over Argentina and Paraguay, real near the border there.
As Columbia moves eastward across the northern Sahara Desert, the crew is now powering up from a power down that the spacecraft has been in for the past 8 days. As the day wears on for the crew, once that test is completed, the standard day before entry and landing checks will be performed. That's a thorough checkout of all the flight control systems, all the systems that Columbia will use for tomorrow's return to Earth, as well as a test firing of all the various steering jets on board the spacecraft.
Columbia, Houston, you have a go for payload bay door closing.
Roger, go for payload bay door closing and work, thanks.
This is Mission Control Houston as we're taking live television from the shuttle landing facility. Entry Flight Director Jeff Bandel is polling all positions here in the flight control room to get a go or no go for the deorbit burn. At this point, it appears that all elements are in place and ready to support a deorbit and entry operation here.
Columbia, Houston.
Go ahead.
And we'd like to give you a go for the deorbit burn at this time. When we pick you up on the other side of the TDRS ZOE, we expect to have some Radicom on the west TDRS while in the burn attitude.
Okay, copy, go for the burn. Houston, we had a good burn.
Columbia, we saw the same thing, good residuals. Columbia, we see you on energy approaching the hack. No change to the KSC weather. Winds are 090 at 5, peak 8. Derotation at 175 knots. You are go for nominal drag chute deploy.
Okay, 175 and nominal drag chute, thanks.
Altitude 58,000 feet. Columbia will very shortly be passing back through the sound barrier and flying at subsonic speeds. As it does so, it'll be sounding twin sonic booms momentarily. And we have confirmation that the crew commander is now taking over manual control of the vehicle. And Columbia is just about to initiate the heading alignment phase. Columbia will be making a right overhead turn of 235 degrees to line up for a south to north final approach and landing. Altitude 30,000 feet, rate of descent 230 feet per second.
Columbia, on energy at the 180.
Roger.
Altitude 25,000 feet, range 13 miles. Pre-flare still underway as Columbia begins to modulate the steepness of its approach to the runway. Standing by for landing gear deployment. And we have main gear down and locked. Final flare. And touchdown, main gear touchdown. Derotation underway. Drag chute should be deployed momentarily. A good drag chute deploy, and there's your touchdown. Columbia returns to its point of origin at the Kennedy Space Center.
Roger, wheel stop, Columbia. Stand by for post-landing deltas, and beautiful ending to a great mission.
Okay, thanks a lot. We're standing by.